Okay, so the problem number 4904. So in this problem, we have to prove that the vector product of two vectors a and b, they are equal to determinant of I, j, r, a1, a2, a3, b1, b2, b3. Apparently a is given as a1, a2, a3 vector, and then b is given as vector b1, b2, b3. So how can we prove that? Well, I just made a simple picture here, which kind of shows the vectors and its position in space. Let's say this is orthonormal basis with vectors I, j, and r. And then this is gonna make it more simple to just visualize its space orientation and find their the cross product in space. So in order to find this, I'm gonna represent this vector product as the corresponding product of their vector decomposition into the corresponding vectors, which is a1i, a2j plus a3r, cross product b1i plus b2j plus b3r. And of course, we know that there is a distribution property between them, so we can redistribute this kind of decomposition into the following formula. We can say that this is essentially a1i cross product of b1i plus b2j plus b3r plus a2j cross product b1i plus b2j plus b3r plus r cross product b1i plus b2j plus b3r. And now we just have to simplify that. So this is going to be a1. There is associative property of scalar multiplication here, so we can just factor this out, and then we have I, which gives us 0, as we know that, because the degree of the angle between them has basically 0 degrees, which is 0, so it kind of annihilates. We can remove that. And then we have a1, b2, I cross product j plus a1, b3, I cross product r plus a2, b1, j cross product I plus a kind of a2, b2, jj. So again, this one annihilates, and then we have a2, b3, j cross product r plus a3, b1, r cross product I plus a3, b2, r cross product j. And then the third term just annihilates as usual, as we already shown that. So what is the cross product of I and r? If you take a look at the right hand rule here, this is the origin. So from I to r, from the end of r, so it looks like anti-clockwise rotation, which is exactly what we need. So this is going to be a1, b2, r, hopefully. And then I, r, following the same kind of logic here, from I to r. This is clockwise. That being said, we have minus j, right? a1, b3, minus j here, and then plus j and I. J from j to I. Again, this is clockwise, so we have minus r, a2, b1, r, j and r from j to r. This is anti-clockwise from the end of I. So we have plus I, plus a2, b3, I, and then from r to I, anti-clockwise. So this is plus j, a3b plus j, and then r and j from r to j. This is clockwise from the end of I. If we take a look from the end of I, this is going to be clockwise rotation. So that's essentially minus negative A3 B2 I. Cool. So we can now factor out these terms. Let's see. Let's factor out I. We're gonna get A2 B3 minus A3 B2. Now factor out J. Let's factor out J. I'm gonna factor out minus J because that's a determinant that's supposed to be determinant A1 B3 minus A3 B1, and I'm gonna factor out R, which gives us A B2 minus A2 B1. As you can see, this is two-dimensional, whatever it is called, the determinant of the second order, I guess that's how it is called in English. I, and then determinant A2 B3. Here we go, A3 B2, and J A1 determinant, and let's say A3, B3 is here, and then B1 is here, plus R, determinant A1, A2, B1, right, and B2. This is the multiplication rule here. And yeah, that looks correct, which is exactly I, J, R, and then A1, A2, A3, B1, B2, B3, using standard decomposition of determinant of the third order. So that's pretty much it. That's the whole proof behind this problem. Pretty easy problem today.